Hey guys, we're going to go ahead and take a look at our next unit of study today, which is rotational motion. And as you can see, we're going to sort of begin by taking a look at what's very familiar to us, and that is things like displacement, velocity, acceleration. Concepts that we're very familiar with from past units are going to come up again here, and the primary difference is instead of dealing with objects moving in a straight line, we are now dealing with objects that are rotating in a circle. And so what we're going to see is that much of the same conceptual language and brain power will be used, but we're going to adapt those concepts to this new paradigm of rotating. And so you can see what's on the screen right now. We have, again, some familiar ideas: the idea of displacement, the idea of velocity, and the idea of acceleration, all three of which have formulas that we learned in the beginning of the year, probably back in September. We also have a little circle here, and the primary purpose of the circle is to make sure that we understand what we're talking about when we are discussing rotational motion and objects moving. So we're going to first begin today by just visualizing what we mean when we introduce certain new terms, and then we're going to primarily from then on focus on learning some new symbols and some new terminology, and relating those new symbols and those new terms to things that we're familiar with in our existing knowledge base about the way objects move. So it'll begin to hopefully make more sense as we get into it here, so we're just going to go ahead and get started. So when we talk about rotational motion, we are obviously discussing objects that spin, and wheels are a classic example of this. And one interesting thing about a wheel is that if you're going to look at every part of the wheel, or perhaps you're going to look at, as a different example, a carnival ride where you have different people seated in different parts of the ride, and the ride is spinning, it doesn't help to necessarily talk about things like displacement or velocity, because with a rotating object, the speed or the velocity of that object is not the same everywhere. So, for example, if we were looking at a wheel right here, the radius of the wheel would extend from the center outward, and what we would find if we were to make careful measurements of the velocity, say, at different points on the wheel. So right here, for example, I have a blue dot, and then towards the end I have a green dot. Well, now what we have to do is visualize that this is rotating. Both of these objects are rotating together because the wheel is spinning. Well, if that's the case, we can ask a question. Which dot is moving faster as the wheel spins, right? So as this wheel just goes round and round and round, between the blue dot and the green dot, which of those two dots is moving faster? And the answer is that the green dot moves faster than the blue dot. And the reason for this is because if you think carefully, the green dot is the dot that's traveling in this big circle here, while the blue dot is actually traveling in a much smaller circle. And since every part of the wheel must complete a rotation simultaneously, it means that you have a large distance, d here, compared to a smaller distance inside here, and then you have the same amount of time. So here we have a certain amount of time delta t, and here we have that same amount of time delta t. So if I have d2, which is larger than d1, then this is going to be a very fast velocity compared to the smaller velocity on the inside. And while that's true, it would be nice sometimes to discuss a single object in terms of its single rotating velocity. In other words, if we have two different velocities at 2 points for this object here, which of course, we're dealing with the blue dot and the green dot, well, that can be confusing because now, if you think about it, Do I really only have 2 points? No, I could have any number of points along this radius here, and all of those points are going to have different velocities. So when we deal with rotational motion, it doesn't always make sense, or certainly it's not convenient to use the idea of velocity, because of the fact that this rotating wheel, well, different points on the wheel have different velocities, right? So we can't talk about a single velocity or speed of that wheel as it rotates if we use the familiar concept of velocity. And remember, the familiar concept velocity was measured in meters per second. So all of these different points along this radius here are going to have different velocities. They're going to be moving at different speeds. They're going to have different measures of their meters per second as the wheel rotates. So for that reason, for the fact that you have so many different velocities along this wheel, we need to measure the rotational rate of the wheel in a different way. In other words, this common method that we're used to, distance over time or displacement over time, is not going to be very helpful. So how else can we do it? Well, if we go back to the idea of having a radius for this wheel, you can imagine this radius rotating as the wheel rotates. In other words, at one moment the line is there, and then later it's here, and then later it's here. So the radius is sort of going round and round as the wheel rotates. Well, we can freeze at 2 different points. So say the radius starts here, so now you have one, starting position. Later on, the radius is right here. And as you do this, you might notice, hey, there's a little angle in here, and we can measure that angle. And in fact, that angle doesn't depend upon the length of the radius. In other words, if I have a large circle or a small circle or a smaller circle or a smaller circle, the radius, or the angle I should say, will always be the same for circles of different radius. And that's really convenient, because what that allows us to do is to look at a change in angle as sort of a way of considering a displacement. So that's the very first thing that we look at, is we say, all right, so because we don't want 100 different velocities along a radius of a wheel, and we want to be able to describe the motion of this wheel in one single term, the angle here is independent of the length of the radius, unlike our velocity, and therefore it becomes very useful for us to try to describe how fast this wheel rotates. So what we're going to do is we're going to go ahead and introduce our first term here, and that is this term delta theta. So instead of delta x, which is measured in meters, we have delta theta, which is not a linear, but rather an angular displacement. So this here is an angular displacement. And instead of being measured in meters, well, since it's an angle, we can measure that in terms of an angle. And you're probably familiar with 2 units for angles, and that would be either degrees or radians. And as you could probably guess, the scientific convention is to use the one that you like less, and that is radians. And, again, you'd probably like that more if you were taught tau instead of pi, but let's move on. Okay, so we have then this first term that we introduced. And just to be clear, we're going to shrink that down just a bit. We have an angular displacement here, and that angular displacement is delta theta, and its units are radians, okay? So there we have our first term. Now, with that in mind, we can then ask the question, okay, so if I have 2 objects that are rotating, how can I tell which object is rotating faster? And that idea of faster, of course, introduces the term time, right? So we now have a time to worry about. So if I want to deal with not an angular displacement, but an angular velocity, right? Then I have to introduce this concept of time. And that concept of time we'll turn our displacement that we established into a velocity. So the symbol for angular velocity looks like a W, but that's technically the Greek letter omega, all right? So this is the Greek letter omega. It means angular velocity, and its units would be radians per second. Oops, I misspelled radians there, sorry. Radians per, oh, that S is hard to draw there. There we go. Second, okay? So we have our second term to introduce here, angular velocity measured in radians per second, okay? And we're going to introduce some equations before we get too far ahead of ourselves as well. So we see here for displacement, we have delta x equals final position minus initial position. And that's simple enough. But angular displacement then is basically the same concept here. So I'm going to go ahead and write that equation. And so we're literally just doing substitutions here. Everywhere we see an x, instead we're going to go ahead and plug a theta. And so then that tells us that our position is replaced with the angle. And so the angular displacement equation simply becomes final angle minus initial angle. And there is our first equation. Okay? So we have our angular displacement equation, which I'm going to squeeze in there, right about there. Hopefully that doesn't ruin your life. All right. So we have that, and then we can abbreviate this term, by the way, so we could just call it rad per s, rad over s. Save a little space here. So typically radians per second we can write like that. And what would the equation for angular velocity be? Well, again, we're just going to make some substitutions. So instead of v, we're going to substitute w over here. And instead of x here, we're going to substitute theta, right? So it really is going to be an exercise in substitution now. So I'm going to go ahead and write that here. And this would be our average angular velocity, and that's equal to the change in the angle theta divided by change in time. So we have another equation that we've introduced. And you could probably begin to guess what our third equation is going to look like here, right? So our third equation, we have acceleration, right? Well, instead of linear acceleration, we're going to call it what? Angular acceleration, right? Simple enough. And the symbol for angular acceleration isn't actually A, it is instead the Greek letter alpha. So you can write alpha by starting at the top, swooping down, and then up, and then down to the right. So top right to bottom left, and then like that. So that's kind of a big alpha. But yeah, so I just typically make my alphas like that. And that is angular acceleration. Right there. Oopsie, that didn't shrink. Let me get that down again. There we go. It's a little bit better. There we go. And the angular acceleration, instead of having units of meters per second, is going to have units of radians per second squared, like that. And then one final thing, of course, would be the equation for angular acceleration. And that equation is pure substitution once again. Alpha, average, the average angular acceleration, is equal to delta v, but we're going to substitute in, for v, we're going to put in omega. So we have delta omega over delta t. Now, it's worth noting that my students of the past have generally been SpongeBob fans, and that's relevant primarily because every class for the last, 8 years or so, has looked at this W, and they've thought that the W here, right, is a really funny looking thing, right? Looks like a W, but it's not a W. And for some reason, because they're SpongeBob fans, they tend to call this W here, this omega, Wumbo. So I'm primarily letting you know that because over the years I've come to call it Wumbo. So as I lecture here today on this video, I might actually slip up and call omega wumbo. So if I do, you know, I wumbo, you wumbo, he, she, we, wumbo. The study of wombology, SpongeBob. It's 5th grade. I don't know what it is. Anyway, you get the idea. So that's the basics of angular displacement, angular velocity, and angular acceleration. Sorry, it's not super neat here. It is tough to squeeze this all in here. I'm going to go ahead and pull our equations down here just to make sure they're nice and neat, one on top of the other. So we have all that, and that hopefully makes some sense to us. Okay, so there are 3 equations for the basics. So what does this all mean? What does it look like? Well, if an object is rotating, right, and there's an angular displacement, the object might start here and it goes over to here. And so the object has moved along the path of a circle. And we can measure that as the angle it has moved, okay? Now, if it does that quickly, right, so if the object is moving really fast, then it's going to have a high angular speed. So the faster it does this, the faster it rotates, the higher wumbo is going to be. And that is the angular speed. And the slower it rotates, then the lower omega average will be the angular speed or angular velocity. And then finally, you know, an object could speed up rather quickly or slow down quickly. So you can imagine a wheel, a car starting from rest, accelerates really, really fast. Then it's going to start spinning fast. And so then you have a large angular acceleration. So basically, you step on the gas pedal, it's going to create a large linear and angular acceleration of that wheel because the wheel's rolling. But that might help you understand what we mean by the wheel, you know, speeding up or slowing down really quickly as it rotates. So we're going to try to move faster here. I know I've been talking a lot, and we have some more equations to get to, as you can see here, so I'm going to try to move quickly through this next slide, so to speak. So as you can see here, we have our familiar kinematic equations. I know you guys love these so much, and I'm sure you were deathly afraid you wouldn't get to use them anymore this year, but yay, they're back. So let's take a look, and what we're going to do is we're going to do a little exercise in substitution. And so everywhere we see an x, what we're going to do is replace that x with what? Theta, right? Everywhere we see a v, we're going to replace it with omega wumbo. And everywhere we see an alpha, I'm sorry, I misspoke. Everywhere we see an a, we're going to replace it with alpha. By the way, my students like to call alpha fish, so that's another fun one. Okay, so we're just going to do some substitutions here, right? And all of the equations then will be the exact same. So this equation that I just circled, the first kinematic, will look the same, except we will make those substitutions. So instead of delta x, we'll write delta theta, a equals 1/2, and instead of vi, we'll write omega I plus omega f delta t. So there we have a very simple kinematic equation number 1. Kinematic equation number 2 looks like this. Omega f equals omega I plus alpha t. So there's our kinematic 2. And these are just the relationships between the 4 terms, right? So then we have delta theta equals omega I delta t plus 1/2 alpha delta t squared. Oopsie. So now we have kinematic 3, and kinematic 4 ends up looking like this. Direct substitution between these 3 terms. So you end up with your 4 kinematic equations, all substituting in for these different terms. You end up with these 4 equations right there. Simple enough. So flew through that. So won't say much more other than, yeah, the same exact relationships between these symbols exist, between these quantities exist, as existed with the linear quantities. So despite the fact that these are all angular quantities, the same mathematical relationships exist, and that's just another way of saying that the kinematics look similar with different symbols, okay? So, almost done. The last bit here, we have a few more terms that we have to introduce today. And as you can see on the left, these are all, again, very familiar. We have mass, we have force, we have momentum. And these are concepts that we've learned about in the past. So the question is, how does this relate to today's lesson and today's idea of rotation, right? So the weirdest one on this slide here is really mass. We are used to mass playing a certain role in Newtonian physics that we've learned about, and that primarily is the role of inertia, right? What does mass tell us? It tells us the inertia of the object. And what does that mean? It means that as an object has a force applied to it, if the mass of that object is very large, then the acceleration will be very small. And similarly, if I apply that same force to a small object, then it's going to have a very large acceleration. Okay? In other words, mass resists acceleration. A mass will resist a force. So, you push a refrigerator, it doesn't move very much. But if you push a marble, it flies off, right? So that's what mass does. Mass has this very important role of inertia. And so an interesting thing about rotations is that the inertia of an object does not just depend upon the mass of that object if we're talking about that object rotating. Another way to think about this is if I have two wheels, right? Let's say I have two wheels and they have the same mass. So here's one wheel and then here's a smaller wheel. Let's suppose I put those two wheels on an axis, right? So these wheels are going to be able to be rotated then, right? So I can rotate this wheel clockwise. If they both have the exact same mass, let's say they both weigh, like 10 pounds. Oh no, I just conflated mass and weight. Well, you know what I mean. They both have the same mass, so on Earth they're going to have the same weight. The point is that they have the same inertia in that case, okay? And so the question is if I apply the exact same force to each wheel, then which wheel is going to be easier to rotate? And the answer is that if I have a massive wheel, let me say that a different way. If I have a large wheel and I apply a certain force to that wheel, then that wheel is actually going to be more difficult to rotate because the fact that the wheel has a larger diameter, even if its mass is the same, the fact that it has a larger diameter means that it will accelerate less for a given force that I apply. And in fact, you might say, okay, well, fine. If it's twice as large, is it 2 times harder to speed up? And the answer is no. It's actually a quadratic relationship. And what that means is if this wheel here has twice the radius of this wheel down here, then it's not twice as difficult to get moving fast. This wheel on the left is actually 4 times harder. So if we have 2r and r, then this is going to be 4 times more difficult to get this wheel moving at the same speed as this wheel. And that can be expressed as the inertia of the wheel, okay? So what we're going to do then is we're going to go ahead and define what we call rotational inertia, okay? So instead of mass, we now have rotational inertia. So an object will have a certain amount of rotational inertia. And that rotational inertia has interesting units. Those units are kilograms times meters squared. And this comes from the fact that the rotational inertia of an object, by the way, this has a symbol. The symbol for rotational inertia is capital I for inertia. And the equation for rotational inertia is actually I equals C times mr squared. And this r squared term shows us that if we double the radius, then the inertia will quadruple. If we triple the radius, the inertia will increase by a factor of 9, and so on. So that's hopefully it makes a little bit of sense. And it's worth noting that C is a constant value, and it can be greater than or equal to 1, but it must be greater than 0. So the maximum value for c, a constant, which is like a geometric, it's a number that is related to how the mass is distributed along the object. But in short, c cannot be greater than 1, and it cannot be 0. It has to be greater than 0. So in any case, this introduces our first term on this page, and that is the idea of rotational inertia. And of course, we need that for our next two equations, right? We have to know something about mass in order to begin to understand force and momentum. So we're going to learn more about these. Keep in mind that this lecture seems like it's covering a lot of topics. It's just very, briefly introducing these topics. What we're really doing today is establishing symbols. So don't worry if you don't understand rotational inertia just yet. What you need to understand is that instead of mass m, we write I, rotational inertia. Instead of force, which is ma, we're going to play our little substitution game again, right? What do I substitute in for m? Well, we just established that's going to be rotational inertia. And what do I substitute in for a? Well, that's not going to be a, it's now going to be alpha. And if I have I alpha, then I don't have a net force, which is a linear concept of the idea of applying a force to an object means I'm going to push on it, right? A linear push. No, if we have a rotational push, there's another name for that, and we call that the torque. And the torque on an object will cause that object to rotate, okay? So we have a net torque here, and it's worth noting that the units of torque are newtons times meters. So if I apply a rotational force, all that means is I'm going to be applying a force some distance away from the axis of rotation. And torque, therefore, has this idea of leverage built into it. And leverage being the idea that, well, if I have a longer lever, right, if I have a crowbar and the crowbar is longer than some other tool I was using, then I'm going to have more leverage. And all that means is that my force will be more effective at causing a rotation than it would have been otherwise. In other words, if I push with a longer handle or longer lever, then that's going to make my job of rotating something easier. So in any case, the units for torque are newtons times meters. So that leaves only one quantity to describe, and that is momentum. And maybe you've been wandering and looking at that equation to figure out what substitutions we make. Well, once again, if we look at mv here, m gets substituted away, and instead of mass, we write inertia. And instead of velocity, we're going to write omega, or wumbo, however you want to say it. And that's the angular velocity, the angular mass, if you will, rotational inertia. And the units for this are going to be, well, the units for angular momentum, which are kilograms meters squared per second. So there are my units. And yeah, we call this angular momentum. And it's got a weird symbol, capital L. I don't know why capital L is the symbol for angular momentum. It just is. A lot of weird symbols here. But in any case, there's our last equation for the lesson today, and that is angular momentum, I omega, which has units of kilograms times meters squared per second, which is a pretty strange unit, I'll admit. In any case, we now have established everything we need to complete our simple assignment today. Your assignment is essentially looking at and making, it's meant to make connections between the linear and the rotational symbols and concepts. So it's really just a couple of tables that you're going to fill out with the information that I provided to you today. So I hope that this made some sense. By the way, I just realized I should have written these out in terms of like plain English. So this torque here is spelled Torque. And then, of course, L, as we said, is angular momentum. Almost forgot to write those down. Silly me. So that's all you need for today's assignment. We introduced lots of new information. You have this right here, so feel free to maybe view this and then immediately complete your assignment for today using the information that we learned in this quick lecture. So I hope this made some sense. Don't worry if you're feeling overwhelmed because I just introduced a whole bunch of new concepts. We're going to be studying much of this independently. So we're going to have a lesson on torque. We're going to have a lesson on angular momentum and rotational inertia. So you have a lot of time yet to learn all this stuff. So I hope you guys have a lovely day and take care.